Thank you for supporting the senior design projects. Our project today is entitled Laptop-Based Wireless Control of a Vehicle. I'm Andrey. We have Paul over here, Pham, and Quan. And first, we'd like to thank the United States Army Material Command for sponsoring this project, because without their help, this project would not have been possible. First of all, I'd like to talk about what our project is and what we actually did with it. Our original project consisted of an RC controller that was able to be run like a normal RC car, with an addition of a data system that could collect sensor data from this RC car through a variety of sensors that were already mounted on it. We wanted to change this analog control into a digital system that could be run through a user interface or a GUI. There were several problems that we encountered with this design and several things that we wanted to change about this analog system to make it more compatible. First of all, data collecting is very challenging because the rapid accelerations due to the analog control. There's a very short amount of time to go from full throttle to no throttle, as well as turning angles. Additionally, the sensor and system data was very, very expensive in the thousands of dollars, and somebody who didn't know how to use an RC control could easily damage the system and cost the Army a lot of money that they didn't really have to spend on a small project like this. Additionally, the data system and controller had very weak signals, and we wanted to increase these signals so that we could run it for a longer range inside and outside. Real-time data was also needed for expositions and shows that AMC wanted to sponsor, so that users would be interested in their actual project. So having a user interface would be very intuitive, and real-time data would be very helpful for this purpose. Additionally, an expensive battery was used to power the data system. This battery was in the range of $150, and this cost was very prohibitive, because if it was run below a certain threshold, it couldn't be recharged. And a price of $150 for a simple dead battery was a very, very high cost to pay. And lastly, we didn't want the user to always have to be in line of sight with the vehicle to be able to run it. So we wanted to implement some kind of remote control system. And these are the solutions we came up with these designs. We were going to send digital signals through the use of a microcontroller to change the acceleration and to smooth the sensitivity. This way, we'll have a running average and a smoother curve when we're running the car. A new controller also replaced the RC control. I'm sure most of you are familiar with an Xbox 360 controller or a PS2 controller. And something like this, everybody would know how to run. And we implemented the controls the same way as you would for any racing game. Amplifiers and antennas also increased the range of our system, and this allowed us to use a higher bandwidth to transfer real-time data to a GUI. And this allows direct user observation of the data they're collecting from the system. Additionally, a voltage circuit and an analog to digital converter allowed our system to measure the voltage of the batteries and inform the user when a low or critical voltage was applied to the circuit. And additionally, this would prevent the battery from going dead. And lastly, a mounted camera with a panning function allowed the user to simply sit at the GUI and to watch what happens with the camera while they control it with the controller. And now I'd like to show several movies of our old system and our new system. Unfortunately, the sound's not working, so I'm going to just narrate it for you. This is our new system. You can see it has the GUI interface, and it has the actual RC car. Now we're going to take it and we're going to run a little test, and you can watch on the GUI what happens. You can see that the user can just look at the GUI and intuitively know how to drive the car without having to be in line of sight of it. You can see you can turn and swivel. And there's a car down the hallway. And now we want to show you a video of the old system. The old system had no interface, and the data was simply stored to the EDAC, which is simply a hard drive that was mounted on the car. So you can see all the old system was just a simple RC control in a vehicle that collects data. You can see how our new system is much more user-friendly and how the interface makes it much more interesting to watch. And with that, I'm going to hand it over to Van so he can talk about our hardware design on the vehicle system itself.
Thank you, Andrey. Now I'm going to talk about our hardware system. As you can see on the diagram over here, there is original system and our modified system. The modified system is built on the top of the original system. and that's use the digital communication to control the vehicle, and also send the feedback to the user. The control signal goes to the antenna and amplified by the bullet to edge, and create the data package sent to the Ethernet switch. The Ethernet switch is the hub of our design. It controls all the traffic to and from the microcontroller, camera, and the index system. We also designed the voltmeter circuit, which allow us to measure the voltage and send the signal to the microcontroller. The microcontroller will analyze the signal and send the control signal to the LCD. The LCD will display the voltage of the battery and also display the system connection status. Microcontroller send 3-pole width modulation to control the servo, turning the camera panning, the servo to control the steering wheel, and the one go to the ESC. And now is our slide for the hardware implementation. As you can see, the car with all the hardware components already integrated on the top of the car. The LCD, the microcontroller, index, the camera, and the bullet amplifier. We also designed the DC converter because the microcontroller and the camera only use 5 voltage to be supplied, and 12 voltage from the battery have to go to the DC converter and fit to one into the microcontroller and the other go to the camera.